So welcome back. The third speaker is Alberto Tacchella, and the title of his talk is The Moduli Space of Linear Control Systems. Please, Alberto.
Thank you very much. So let me start by thanking the organizers for organizing this conference, first of all, and for inviting me. So as you probably know, I was a PhD student of Claudio's. I started my PhD in 2006, and this is 16 years ago. And realizing this had quite an effect on me, because it's really a lot of time. So I did my PhD at the mathematics department in Genoa, but I was coming from the physics department, and I knew very few people in the maths department, perhaps 3 or 4 of them, and Claudio was not one of them. And so I got, it sounds incredible today, but Claudio at the time was the coordinator of the PhD program of the mathematics department, and so I got assigned. I got him as a supervisor more or less by default, because I didn't know anybody, and so Claudio said, "Okay, I will be your supervisor for now." It was supposed to be a provisional assignment, and then at the end of the first year, I should have chosen an advisor. But then there is a saying that goes like this: in Italy, nothing is stable except the provisional. And this is quite true in this case, because that provisional assignment became the final one. And so one thing I remember particularly in those initial months is that so there was you had to take 3 PhD courses in your first year, and there was this list of PhD courses. Claudio made one of them, and then I was uncertain, because there was a course about PDEs, which was a familiar topic for me as a physicist. And then there was a course on algebraic geometry. And then I told, in one of our first meetings, I told Claudio about this, the fact that I was undecided. And Claudio said, "Oh, come on, let's follow the course on algebraic geometry. Who cares about PDEs?" And then I did follow that course. It was quite a shock, because, of course, I was a physicist. I barely knew what a ring is. And then I was in the middle of a PhD course in algebraic geometry. But it was quite useful for my later career. So it was the right decision after all. And I wasn't going to be an analyst anyway. So definitely the right decision. But okay, now enough with the preliminaries. Let me go to
an advisorship. It seems, told in this way, a dictatorship from my part.
No. I mean, it was actually no. I mean, you were doing your job, right? Okay, but now let's come to the topic of this presentation. And it's a very classical topic. I will speak about, let's say, linear differential equations, so to speak, but viewed from a very particular angle. So here's the plan. I will start by explaining a bit what linear control systems are. Then there will be an interlude about quivers and the representation theory of quivers. It will be very quick because, of course, it's impossible to say anything in a presentation like this, but just to refresh the topic. And finally, I will show you how you can use the theory of quiver representation to build modular spaces, let's say, for linear systems. So, as you may know, I lately have been spending a lot of time with engineers, not only software engineers, but also real mechanical engineers. And there has been a bit of a cultural clash because sometimes you talk about a topic, but they have a different opinion of what that topic is. So, for instance, I thought I knew what a linear system is, right? A linear time invariant, let's say, dynamical system is a system of linear differential equations. So you have some coordinates, x1, xn, and a bunch of ODEs with, since we are all grown-ups here, this can be written in a more compact way using matrix notation. So you have this x dot equal ax, where the x is lives in a n-dimensional, let's say, real space, and A is a matrix. But then it turns out that engineers usually think about dynamical systems in a very different way. Namely, they think about an input signal, which is a function of time in a certain space R to the m, which is the space of inputs of your system. You have an output signal, which lives in another space, R to the p, which is the output space. I is just an interval in the real line. And then a dynamical system is a device, let's say, mapping input signals to output signals. So there is this very different perspective, and if you make suitable assumptions, in which, for the case I'm interested in today, include linearity and time invariance, you can actually translate this description into a so-called state space realization, right? So you introduce the linear space R to the n, which was not there at the beginning, and you describe your system in terms of the time evolution of a state vector that is an element in this space, according to a differential equation of this form, where now you don't have only the matrix A, but you also have a piece that depends on the instantaneous input. So this is not a signal, this is just, U is just an element of the input space. And you also have the instantaneous output, Y, which is a function of the state and the input. So you see, it's a very different description, right? You have a lot more stuff going on. You have these matrices B, C, and D, which was not there before. Here, of course, A, B, C, D are just matrices of the appropriate size. The notation here is sort of standard in the control theoretic literature. You have this M, N, and P, which are respectively the dimension of inputs, state, and outputs. So yeah, there are some puzzling aspects. First of all, the evolution law, this is not an autonomous system anymore, right? The evolution law of your state vector depends on the input, which is unknown a priori. So it is not an autonomous system. And also the presence of Y is a bit puzzling because it doesn't enter into the evolution equations. So one could say, well, but why? Why bother? The point is that underlying all this, there is a sort of a change of paradigm from closed to open systems. So this is an example of an open system, a system which is primarily defined in terms of its input-output relation. So generally, we can say that open systems are characterized by the presence of interfaces that let you compose them. And this is what engineers do, right? They build a complicated system by composing together simpler blocks. So in this case, for instance, given a linear time invariant system as the one I introduced above, we can call the pair MP its interface, that is dimension of input and dimension of output space. And then we have multiple notion of composition at our disposal, at least two. We can compose two systems in a series, which means we attach the outputs of the first system to the inputs of the second system, and this only works if the two interfaces are compatible, namely the number of output is equal to the number of input of the second system. And there is also notion of parallel composition, which simply means putting the two systems together and treating the inputs globally and the outputs globally as a single system. So this is a quite popular topic in the last few years. The theory of open system has been studied using tools from category theory, basically. Surprisingly, it can shed a new light even on old subjects like classical mechanics. For instance, there is this very nice recent paper by John Baez and collaborators, which speaks about this notion of composition in classical mechanics, where you usually don't adopt this perspective. Okay, but this is not actually the topic of my talk. This is just to introduce and to explain why it's important to consider this kind of systems. So let's go back to our state space realization. You see, as I was saying before, if we adopt this viewpoint, it means that the state vector is in some sense less real than inputs and outputs, right? Because it was not there from the beginning. It's something we put in. And mathematically, this corresponds to a very precise fact. It corresponds to the fact that X is actually not meaningful in itself, but it is meaningful only in a geometric sense, that is up to a change of basis in R to the n. In other words, the single numbers the single components of X has no meaning. It's only the vector which has a dynamical meaning.
Sorry, Alberto, I don't understand why the same is not true for U and Y.
The same is not true for U and Y because typically you don't put a linear. I mean, for instance, the inputs, yes, are elements of R to the m, but you don't use the linear structure of R to the m. You take each input separately. For instance, you cannot typically swap them, right? For instance, if you want, they are labeled vectors. So
okay, thank you.
Yeah, but I will go back to this later.
Saying that this, I mean, the linear system is just a class where A, B, C, and D are defined just up to.
Yes, exactly. There is an identification between state space realizations.
Well, it's written down. Sorry,
yeah.
I was fixed on the first 3 lines and thinking, and I didn't read the rest of the slide. Sorry. Yes.
Yeah. I was exactly going to talk about this. So you have a notion of equivalence between this kind of realizations, which is given exactly by this operation of base change in the state space. And in terms of the matrices A, B, C, and D, it acts in this way. So let us call an equivalence class of quadruples under this action an LTI system of signature M and P. And this is the object that we are interested in classifying, right? Not realization, but the real thing, the system. So the goal is to build a space that parameterizes the different possible LTI systems of a given signature. But before going to this, this new viewpoint of open systems makes natural to consider new properties that are not usually defined in classical mechanics when everything is autonomous. So, for instance, well, first of all, linear systems, as you very well know, are explicitly solvable. You can write down the flow map of a linear time invariant system, which here I call phi. Here the arguments are the initial time, the initial state, and this last R here is the evolution time. And you have this nice formula that gives you the time evolution of the system for any given initial point. It's usually called Lagrange formula. I don't know if it was even written down by Lagrange. I didn't do my homework on this, but let's call it in this way. So you have this definition which says that a system is controllable or completely controllable if for every initial state you can reach zero. There is a time and an input signal that makes you reach zero. Okay, so in fact, this is you can take actually any other state apart from zero, and the notion is the same. So this is clearly a very important property of a control system. And then you have this very nice criterion which says that a linear time invariant system is controllable if and only if this block matrix that you build by stacking together horizontally the matrices B, A times B, and so on up to A to the n-1 B has full rank, which means rank n. So this is a well-known criterion in the control theoretic literature. Of course, notice that it is invariant under the GLN action, right? Because when you change basis in the state space, there is a factor of G on one side of B, but then you have a factor of G to the -1 on A, and these two cancel out. And then there is this other notion, which is observability. A time invariant system is a linear time invariant system is completely observable if for every initial state there is a time such that we can reconstruct the initial state knowing only the output signal from time 0 to t. Not the state, obviously. when the evolution, of course, is when you consider evolution with the input equal to 0, which is also called the free evolution of the system. So this is a complementary property, if you want. And again, it turns out that there is a nice criterion for this. In this case, you build this other matrix, which is called observability matrix, by, again, stacking together matrices, but this time you use C, which is, of course, the matrix that defines the outputs. And C A to the I for I that goes to 0, from 0 to n-1. And again, this is the system is observable if and only if this matrix has rank n. So these two results look very similar, and indeed they are basically the same result, because it turns out that there is a duality between linear time invariant system, which is defined by this map here. So you transpose A and D, and you transpose and interchange the input matrix and the output matrix. And observability for one system corresponds to controllability for the dual system, and vice versa. So there is this very nice duality. Okay, but now, as I was saying before, our goal is to build moduli spaces for LTI system. And in order to do this, okay, this is actually a very well-known problem. There is a huge literature on this, but what I want to show you today is that this problem can be tackled by using the representation theory of quivers. So let me remind you very quickly, although I guess most of you know very well about this, but let me remind you about the theory of the quiver representation. So this is always the same slide that I keep pasting in my presentation for the last 10 years. A quiver is just another name for a directed graph without limitation on loops or multiple arcs. So this is an example, very simple actually. What is a representation of a quiver over a field? Well, it's very easy. For each vertex of the quiver, you take a vector space over K, and for each arrow, you take a linear map from the corresponding vector space to between the corresponding vector spaces. So in this case, for instance, we have two vertices, so two linear spaces which define the so-called dimension vector, right? Because finite dimensional vector spaces are basically indexed by their dimension. And in this case, so the two arrows here, you have one loop at 1, which corresponds to a matrix D1 times D1, where D1 is the dimension of the vector space at 1, and the other arrow corresponds to a matrix D1 times D2. And you have a notion of isomorphism of representation, which means that you require that you have a family of linear isomorphisms between the vector spaces associated to each vertex. This, of course, implies that the dimension vector must be the same. And then you act with an algebraic group GD, which is just a product of general linear groups, one for each vector space. And you act on the linear maps in the obvious way by change of basis. There is this factor by K star because this section has a kernel actually, because the scalar tuples of scalar matrices act trivially by change of basis. So to get a faithful action, you need to kill this kernel. So the goal of representation theory of quivers is to classify the possible isomorphism classes of representations of a quiver for fixed dimension vector, for any fixed dimension vector. So here we can introduce some definitions. So we can say that a quiver is of finite type if these isomorphism classes are finitely many. Of course, one is mainly interested in the composable representation, because those are the basic blocks that let you build all the representation. And then for quivers, well, this is not true. So there are infinitely many isomorphism classes in the composable. That you have this further subdivision you call Q tame if you have a finite number of families of dimension at most one of isoclasses in the composable. And then you call it wild if, not if it's not tame, but if there are arbitrary large families of non-isomorphic in the composables. Now this is a bit strange, right? Because these two classes are not complementary, but one can actually prove a so-called trichotomy theorem, which says that this partition is actually exhaustive, because if you have a quiver, finite, connected, and so on, which is not of finite type, then it is either tame or wild. So there is this strange phenomenon that if your quiver is not tame, basically anything can happen, right? You have these arbitrary large families of representations. By the way, this is not the whole story, because there is you can also say to which class each quiver belongs just by looking at the graph, at the underlying graph of the quiver. But okay, we will not dwell on this topic, because the fact is the quivers we shall be interested in are typically wild. So we are in the worst possible case, and then the basic tool becomes geometric, right? Because we have this quotient space. The space of representation is, generally speaking, a vector space on which you have the action of this linear reductive group. This is very important. And then we would like to build a quotient of this action. But the problem is that the topological quotient is generally badly behaved, because this group will have, for instance, open orbits, and open orbits means open points in the quotient, right? So the quotient space is not T1, not Hausdorff. So there are many ways to remedy this and to build good quotients. I will briefly talk about two of them, because we will need them both in the sequel. One option is simply to take the so-called categorical quotient. So this is the affine scheme, which corresponds to the ring of invariant functions on this vector space. In this situation, this scheme is even reduced, so you actually get an affine variety. And the basic results in these settings are these. First of all, the fiber of the projection map of this quotient, each fiber contains a unique closed orbit. And then you have this result by Michael Artin, which says that an orbit is closed if and only if the corresponding representation is semi-simple. So putting these two facts together, we see that this affine variety that we get in this way parameterizes isomorphism classes of semi-simple representations of your quiver. So this is useful, but sometimes you want a finer parameterization that discards less orbits. So there is another more fine-grained approach to this problem. In this approach, you trade invariants, which are not sufficient, because with invariants you get the categorical quotient. So you trade them for semi-invariants, that is, functions that have this kind of behavior with respect to the GD action, where chi is some fixed character of this group. Of course, the drawback in this case is that your quotient will depend on the choice of the character. It's no longer universal, so to say. So in the present setting, the characters of the group, this group GD that I mentioned before, the product of general linear groups, are all of this form. They are products of determinant, the determinant function on each factor, to some power, to some integer power theta I. So they are basically described by an integral vector, theta. Here, Q0, of course, is the set of vertices of our quiver. And then you also want this condition, this orthogonality condition between theta and d. This again has to do with the fact that there is this kernel in this group that you must kill. So at this point, to make a very long story short, because of course it's impossible to summarize this on a slide, but what can you do? You can define a notion of theta stability and theta semi-stability for the points of your representation space. And then you do, using some standard construction, you can get a variety, an algebraic variety, which is quasi-projective in general. Here I called it MQD theta. As I said before, it depends on this theta, which is also called the stability parameter, plus a quotient map whose domain is not the whole representation space, but the set of semi-stable points. Okay, so you have this quotient on the semi-stable points, and the stable points are an open subset on which the group GD acts freely. So in this case, you see, you get, in a sense, you get more points, but at the price of depending on this parameter. Okay, so now let us return to our setting of linear time invariant system, right? Because now what we would like to do is to interpret the data defining a state space realization of an LTI system as the representation of a quiver, okay? And we have two things to match, actually. We have the data, the linear data itself, but also the group action. So the linear data is this quadruple of matrices here that we saw before. The action is this one. So first of all, we can get rid of the matrix D because it is fixed by the action, because D doesn't involve the state, right? So to get rid of this, we just factor out this last piece of this last matrix space, and then the action only affects this V, M, and P, this vector space that I defined here. Or in other words, we have a trivial bundle, right, on the space of P times M matrices, and we are interested in the fiber of this trivial bundle. So we fix D equal to 0. This D, if you remember, is the map that takes inputs directly to outputs without passing through the state. So when this is 0, you get what is called a strictly proper system, meaning that these are the systems where the instantaneous input does not affect the instantaneous output, right? You can only affect the output going through the state. So let us focus on this quotient of this vector space by this action. Now, it seems that there is an obvious candidate, right, for interpreting this as a problem of quiver representations, because after all, the matrices A, B, and C define 3 linear maps, right, between these 3 spaces. And so you could say, okay, it's very simple. Take this quiver and this dimension vector. What could possibly go wrong, right? Well, no, actually, this is wrong because this group GD which is built only starting from the dimension vector. In this case, it turns out it's too large because you change basis in every single linear space, right? So you get these 2 factors which should not be there, and this goes back to our previous observation that change of basis in the input and output space should not be allowed. You don't want to exchange 2 inputs in a system, right? Because sometimes when you exchange, for instance, 2 wires on an electrical component, in a way it works. If you exchange the wires, it explodes. So this kind of change of basis is not allowed. So let's try again. What we do here is we take the matrices B and C and slice them. We slice B into column vectors and C into row vectors. Okay. Here I'm using this notation, which is hopefully self-evident. B star 1, for instance, means the first column where you fix the index, the column index of B to 1, and similarly for the other cases. And then you take not a single quiver like before, but a family of quiver indexed by M and P. Again, this is sounds right, because remember that the pair MP is the famous interface that I introduced at the beginning. So we are basically fixing the interface of our system and building everything relative to this choice of interface. And here in the quiver, I'm using again a convention in which double arrow means a bundle of arrows. So this quiver is made by taking M different arrows from 1 to 2, then the loop at 2 that stays the same, and P different arrows from 2 to 3, corresponding, of course, to the column of B and the rows of C. And now the dimension vector, of course, is 1 and 1, because the vertices at 1 and 3 are one-dimensional. This is actually an old trick which is known as framing in other contexts. But again, we have a problem, actually, because now if you build the group GD, in this case, things are better, but still not okay, because we have 2 factors of R star, which are these alpha and beta here, which act in this way. And the quotient by the kernel of the action eats up one of the 2 parameters, but the other remains. So it's still, this group is still not isomorphic to GLN. And so finally, what we do is to fuse together the vertices 1 and 3, Okay, the two one-dimensional vertices, we fuse them together. So now the arrows, the input and the output arrows are opposite. This, of course, doesn't change anything with respect to the linear data, because we did slice the matrices before. But now we have a problem. Well, no, just kidding. We don't have any problem. In this case, the group GD turns out to be really isomorphic to GLN. And by the way, let me note in passing that this QMP in this latest revision is an example of a so-called generalized frame quiver, notion which was introduced in a paper by Claudio and co-workers, and which was published, by the way, in a special issue of the Journal of Geometry and Physics in honor of Ugo's 60th birthday. So it's particularly appropriate to cite it today. Okay, so now we have the right quiver. We can use it to obtain a description of the moduli space of linear time invariant system. So first of all, let us consider the so-called minimal case. Minimal means a system which is both controllable and observable. Okay, so both the conditions that we saw before. And then we have this theorem which says that if we take a tripole of matrices A, B, C and consider the system realized by these matrices, this is minimal if and only if the corresponding point in the representation space of the quiver we defined before with the dimension vector 1n is simple. Okay, is a simple. So you have this beautiful relationship between control theoretic properties and representation theoretic properties. So I can actually sketch the proof of this result because it's quite easy. Also, Filippo some days ago said that every presentation should have a two-line proof. Here's four-line proof, but I hope you don't get lost anyway. So the gist is that if you take a proper sub-representation of this point, that you have two options basically. You can take a sub-representation of dimension vector 1k with k smaller than n, but that would imply that the rank of the controllability matrix is at most k, and this contradicts controllability, of course. Whereas if you take a proper sub-representation of dimension vector 0k, so you decrease also the dimension of in the first component, and k again is, of course, it cannot be 0 in this case because the sub-representation must be proper, but it will be less than n, surely. Then this implies that the rank of the observability matrix is at most n minus k, and this contradicts observability. So there is actually a very close link between this property of simplicity and minimality. Now, it's a general fact that the isomorphism classes of simple representations form a Zariski open subvariety inside the categorical quotient. And also, you have this very nice formula which describes the dimension of the categorical quotient. Again, this is only valid if you have simple representations, basically, but we are in this case. It says that the dimension of the quotient space is 1 minus R dd, where this R is the so-called Ringel or Euler-Ringel form associated to your quiver. This is an integral bilinear form which is built using the adjacency matrix of the quiver, basically. It is like the identity minus the adjacency matrix, I think. In this case, this Euler-Ringel form has this form. So if we plug the dimension vector 1n inside this formula, we get n plus p times n. Okay, so this turns out to be the dimension of this quotient. So summing up, we have this theorem, which of course was is known in the literature, but here is derived using the tools of the representation theory of quivers, which says that the moduli space of minimal linear time invariant system is quasi-affine variety, because it's a risky open into an affine variety, so it's quasi-affine, smooth, and of dimension n plus p times n. Okay, so this was one example, but then you could say, okay, this is for minimal system. What about systems which are just controllable or just observable, not both of them? Well, in this case, it is useful to go to the second approach that I showed before, the one using stability parameters, okay? So, what are the possible stability parameters for our family of quivers? Well, the dimension vector is 1n. And also we have this constraint that of orthogonality. So basically there are two choices, right? You can take minus n1 or n minus 1 up to common positive factors. And it turns out that stability with respect to these two possible choices, again, closely mirrors the system theoretic properties, because this time you have that this point here corresponds to a controllable system if and only if it is theta plus stable, and corresponds to an observable system if and only if it is theta minus stable. So again, you have this closed link between system theoretic properties and geometric properties, like stability with respect to a given parameter. And then you can crank up the machinery that I briefly recalled before, and obtain realizations, if you want, of the moduli spaces of controllable and observable linear system with a given signature, using the algebra geometric approach that I was describing before, right? For this choice of the stability parameters. And this immediately implies, again, something which was already known, but it's nice confirmation that these two moduli spaces are quasi-projective varieties. Okay, so let me check. Okay, so let me mention another interesting result along these lines. So let us denote by GRK infinity the Grassmannian of k-dimensional subspaces in a linear space of countable dimensions. So this, I think, this is the same Grassmannian that Letterio was talking about before, but I'm not sure because there are many versions of infinite dimensional Grassmannians. But anyway, this is a fairly standard object. And it turns out that we can embed these moduli spaces that I defined before into this infinite dimensional Grassmannian. So you have this theorem due to Le Brun and Reinecke, which says that there is an embedding if you take the disjoint union of all the moduli spaces of systems of signature M and P over N. So you're taking all the system with a given interface and with state space of any possible dimension. You can embed this joint union into this infinite dimensional Grassmannian, and there is an explicit description of the image of this embedding. You can describe it as a union of some affine cells. You know, Grassmannians have this decomposition in standard affine cells, right? Where you take index set and you take matrices of a certain rank which have prescribed values on the corresponding columns. Okay, so I'm not going to recall this now, but it's a very well-known cell decomposition of Grassmannians, and you have that the image of this embedding is described by this straightforward property. And of course, now you can use the duality between controllable and observable system to obtain another embedding, which starts, in this case, from the modular space of observable system. Again, with the disjoint union over N. Of course, the conditions vary a bit, but and let me add a note about this, because in a paper that you can find on the archive, Le Brun has used these two results to argue that these two moduli spaces, M control and M observable, are defined over the field with one element, F1. Not only that, but are related to the spectrum of Z over F1. At least using one approach to the geometry of F1. There are many of them, and I don't know if they are equivalent, but I wanted to mention this result because Claudio has worked on this, has published on the field with one element recently, so it's a nice relation. Okay, let me conclude by mentioning a very special case, which is the case of so-called single input, singular output systems, or SISO, namely M equal P equal 1. This is exceptional, okay? This is exceptional because, for instance, if you take the modular space of controllable system, with the state space of dimension n, you find that this is isomorphic to an affine space. So it's not only quasi-affine, it is even affine. 2n dimensional, of course, according to the formula we derived before, right? M plus P times n. And the quotient map has even an algebraic section, which is very well known among control theorists. It is the so-called canonical control form for a linear time invariant system. So this is actually very well known, right? Because you see, A is just what is called usually called the companion matrix, which means that and B is the cyclic vector for A, right? Okay, so you get all n times n matrices which admit a cyclic vector, because you can prove that the two things are equivalent. And the reason for these strange names for the non-zero, for the variable entries of the matrix A, this A0 and 1 and so on, is that they are exactly the coefficients of the characteristic polynomial of A. where AI is the coefficient of t to the power of I. Okay, whereas C is free, is just n parameters, n free parameters. So this is a very nice result. Unfortunately, it doesn't generalize because when you have more than one input, Hayes-Winkel proved that this modular space is never projected. And it follows that when for multiple input system, there is no hope to get global algebraic canonical forms. So this is not bad news per se. It just means that the geometry of these varieties is even more interesting when you have more inputs. But it explains why in textbooks on control theory, the single input, single output case is usually treated in a lot of details with the canonical forms and everything. But when you go to multiple input, multiple output systems, everything is more hand wavy, and they say, okay, there is also this case, but you can refer to monographs and research articles for this case. We are not going to treat it in this book because indeed it is more complicated. Okay, so I should end by apologizing with everyone who read the abstract and thought this was about non-commutative geometry. Of course, the initial idea was to link all this stuff to developments in non-commutative geometry, but it was I reworked a bit the presentation. I mean, this is work in progress, and it's not ready yet for a talk, but I'm working on it, and judging from the recent rate of progress, I think that I could speak about it for the conference in occasion of Claudio's retirement. It happens when he's 70, right? Because, it may happen before, and with the new government, we could get quota 102, quota 103, I don't know. So, but assuming it happens at the regular age, it could be done. Okay, so let me end with this slide. Thank you very much, Claudio, for all the stuff I learned, and happy birthday.
Okay, thank you, Alberto, for the very interesting talk. Is there any question?
So thank you, Alberto, for this talk. I assumed wrongly that I knew not everything, but a lot about linear system. This is not the case. So I have to rethink about linear system. So my natural question, the question I was thinking about was precisely about non-commutative realization or a version of this story, but we can talk about that, I think. And so I have a second question, which is this one. So you realize, I mean, the moduli space controllable or observable LTIs by means of a moduli space of stable representations with respect to a certain parameter. And so a moment map is involved in this construction, right? You can think of this also from the symplectic point of view.
Maybe.
And well, I would like to know if this moment map has any meaning in terms of the classical theory of linear systems.
Well, I don't know actually, because these moduli spaces are not symplectic reductions, right? They are
They are
built.
not,
They're
because
not symplectic reductions, right?
I don't know. This is, they are Poisson. They are
No,
not.
no, they're built with this proj construction. I mean, using the machinery of King.
Of King, but in
So,
some sense should be a symplectic or Poisson version of.
no, it's possible that you can get them also by symplectic reduction. This is something I didn't investigate, but it's possible that, because this is another way, right, to get good quotients in such situations. So maybe there is a description in also in those terms.
Well, because your construction is over C, no? Essentially.
Well, it works on any field. This is actually a delicate point, right? Because usually for representation theoretic reasons, you want to work over C, but then people engineers will get very upset if you propose a system which has a complex valued matrices, right? So actually, the field is important, and I think the fact that these matrices are defined over R and not over C plays a role in this story.
Yes, this is not clear, but by the way, because I don't know if well, there is some, at least some step where the fact that the field is algebraically closed plays a role. I think I don't remember all details in this moment, but I guess that.
No, but I mean, for instance, King's construction works on every field, so.
So you don't
But
need.
you have to be careful because, of course, depending on the field, you will get different modular spaces. So.
Or non-emptiness, for example.
Exactly.
Okay, thank you. Okay. So we have something. We'll be back in Genoa shortly. You will you be back in Genoa shortly?
Not shortly, but I guess for Christmas.
Short.
Yeah.
Christmas. Okay.
Shortly.
Yeah. Okay. Is there any other question or comment? Okay. Otherwise, we thank Alberto again. And so it's Pinot time.